contribution that maybe could be useful for some numerical simulation. So it's about talking about interfaces, mechanical interfaces only. Okay, this is a parenthesis. I found this nice painting in one of the gallery in the Uffizi Museum in Florence, and is dedicated to mathematics. At the center, a kind of complex structure, including the firmamentum, and on the bottom is the portrait of Galileo. So I thought it would be interesting to show this representation of basically geometry is this. Okay, so I'm talking about zero thickness interfaces. This is a model that was introduced in the 60s by Blatt and Dugdale. And basically, the idea was to regularize singularities that come out with the since then, thousands of models for interfaces have been introduced. What I'm talking about is not the 1,000+1 model. I will show some equation, but the idea is to focus on 2 points. One is a thermodynamic derivation that allows the model to be matched with the continuum formulation, and that can be useful when you want to force unilateral conditions. And the other one is, okay, and I will show. So the first is to derive the model from the thermodynamic consideration that allow to introduce either several phenomena that can be observed, like degradation, damage, also irreversible permanent openings. Okay, these two. What happens? And the other would be the possibility of including unilateral interfaces with in a strong form, and especially the one possibility of modeling the latency with the rule derived from the dissipation potential without including ad hoc hypothesis. So the idea is this one. When you have friction, you have asperities. So the asperities compose some dilatancy, but asperity wear out with time. So the idea is try to model this phenomenon directly in the formulation. What happens here? Okay, directly in the formulation of the model. Cohesive interfaces are based on this classical scheme. So we have partial opening. So we have kinematic variables, which are basically displacement, and I add the damage variable. Damage variable in this case is just one single scalar variable. The dual variables are the stresses, the attractions on the interfaces, and the damage variable, which has the meaning of release energy. The power is the product of the dual variable, so the traction times the displacement plus the damage variable times the release energy. And we can split the power in the sum of the reversible and a dissipation part. This is all these small displacements, by additively decomposing the kinematic variables in the damage and the elastic, so reversible and irreversible part. It is interesting to see what happens with the, this is damage variable, which is split in the elastic and the plastic part. The sum is 0, because this product must contribute to nothing in the overall power, because the overall power is just given by the mechanical power. So this is like an internal what's called distortion of the micro structure. So we have basically the internal energy this is the classical term with some stiffness matrix. There's something missing here, okay. And this is damage part. And these are some indicator function that enforce the limits at on the damage variable that is constrained to be between 0 and 1. Some additional terms can be added. For instance, this one can be used for accounting for fibers eventually present in the microstructure, and some more special can be used in order to enforce unilateral behavior if one wishes to. So we have from the internal energy the instructions and the damage variable, and the release energy is dual damage variable. The function now is obtained in a standard form using Germain-Nguyen classical standard generalized material. So this is the Clausius-Duhem inequality, and we introduce a distribution functional which has to have these properties, and it turns out to be the support function of the domain of the admissible stress. By the Frenkel conjugate, we obtain the conjugate dissipation function, which is the indicator function of the domain of the admissible stress. So everything can be defined if we define this domain. This domain is simply the activation function of the interface. And the subdifferential of this indicator function gives the flow rules for the inelastic displacement and for the damage variable. Now I introduce a kind of activation function, which is now if this is mu is the frictional coefficient, and so if you erase the dependence of the frictional coefficient and on this normal stress on the damage variable, we have some classical Coulomb type activation function. What I do, first I introduce a dependency of the normal stress on the damage variable, but also the frictional coefficient depends on the damage variable. That the damage creates both a degradation of the resistance, but also of the frictional angle. This is using some form. This is some form, not necessarily. It's nothing special. This form. You just know that to make some example. This is the representation of the surface. These are the cross section of the surface with the plane. This is with the normal stress damage variable. So it's a vertical cross section. This is the cross section in the sigma tau plane. This is the cross section in the tau damage variable. So these are the cross section here. What is important is that, for instance, this curve. Nope. No. Okay. This curve is not the limit. Is not like a more Coulomb boundary, because for any process, the three variables, the normal stress, the tangential stress, and the damage variable evolve together. So the stress path is described by a curve in this space. So there is no physical process that is described by the curve in this plane. So, okay, the other flow rules are not so important. Oh, no, one thing is important here. This model has an internal length. So this is different from mostly, is an additional difference from mostly interface model. We have an internal length that spontaneously occurs as this ratio between the, this is the fractured energy, and this is the something related to a limit stress. It's related to cohesion, actually. And this expression is similar to the internal length that occurs in fractional mechanics. In that case, we have the square of the fractional energy divided by some limit stress multiplied by Young modulus. We don't have Young modulus in this case. So just to make some example of how it works, this is a monotonic load history in mode 1 fracture. This is, so we have only normal traction and damage variable. This is the, for some values of the, for the parameters, this is the load path in this plane. When this loading path hits the boundary, which is this point, we have the limit stress, the limit damage variable, which in this case is fractional energy. It can be demonstrated in this case the fractional energy, this zeta 0 part is right, is exactly the fractional energy in mode 1. And then we, after going on, increasing the normal opening, we go back on the limit surface, and we describe the classical degradation. So this is the maximum stress and some degradation. And in this case, unloading results in damage without permanent deformation. This first step, in this case, I use a finite compliance, finite stiffness, can be also avoided, but anyway, it depends on the choice of the internal energy. It's also possible to have okay, if we use this, in this other case, we meet the activation surface in a point like this. Since the flow rules are normal flow rules, if we develop contemporary opening and damage. So in this case, when we unload, we have both degradation of the stiffness and some permanent deformation. And this here the load we follow, in this case, in the traction damage release energy space. This is the evolution of the damage parameter. Upon unloading, it stays constant. Okay, and these are some calculations that are not so important. In the sliding process, we have something similar. In this case, we have degradation and permanent deformation. It's very similar to the previous one. What is interesting is that this is a process where I imagine to have only sliding and not allowing normal displacement. So what happens is that this is the evolution of the tangential stress, and this is the evolution of the normal stress. So we have some normal stress occurring because I have the latency, which is precluded, but since the friction angle is degrading, this normal stress after a peak goes back to 0. And if you look at the number, so this is 1.2 and this is 0.04. So very small, and eventually goes to 0. So this is what I said before. These colored lines are actually the contour line, ISO damage contour line that can be obtained from following different paths with different ratio between the normal and tangential stress. So this is the blue line, which is here, is the line for 0 damage. Then the other line corresponds to higher damage, and you can see that the friction angle tends to 0, rapidly to 0. So if we plot the the dilatancy angle for different values of the ratio between the normal and tangential stress. It starts from a non-zero value and tends to zero with more or less rapidly. This can be made also even, well, there are parameters that govern this degradation exponent, which in this case I think is 1.5, but we can take it later. Finally, just to show that it can work, there's a very classical test made by Sanzadeh. What he did was doing some experiment on should be mortar. It was first creating a crack in extension up, but with not allowing a complete opening, and then the sample. And these are the for two different opening. The prediction, no. Okay, the prediction of the tangential stress and for some for some of the ratios between normal and the tangential displacement, the point at the experimental values. This line is the prediction of this model, which is pretty good. This is another case. Though this is for normal stress, this is for tangential stress. If tangential stress works, the normal stress actually works pretty well. Tangential stress, well, I think the peak is quite okay. The maximum displacement is quite okay. This is not perfect, but anyway, it's promising. Besides, this is just constitutive. The experiment, of course, were be done with some more refined geometrical model. Okay, these are the conclusion, and so anyway, so the interesting things about this thermodynamic basis, this degradation of the interface, and the fact that the model has an internal latent, which is very interesting because it can be reproduce some of the effects which are expected in fractional mechanics. Okay.